In 1961, astronomer Frank Drake calculated that our galaxy should contain at least 10,000 communicating civilizations. Yet after decades of listening, we have heard nothing but cosmic silence. It's as if the universe is playing the ultimate game of hide and seek with billions of players who have all found the perfect hiding spot. But this is just the tip of the iceberg. Tonight we explore 100 interstellar mysteries that reveal just how little we understand about the cosmos around us. From objects that shouldn't exist to signals that vanish without explanation, each puzzle brings us closer to a startling realization. Stay with me until the end, because what we discover might change everything you thought you knew about our place in this strange, silent universe. And if you enjoy drifting off to scientific wonders, feel free to subscribe or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let these cosmic questions carry you. And if you're ready, let's begin. Strange visitors from beyond. In October of 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something unprecedented. A faint streak of light moving through our solar system, but not like any comet or asteroid they had ever seen. They named it Oumuamua Hawaiian for scout or messenger, and it would become the first confirmed visitor from interstellar space. What made Oumuamua so strange was not just its origin beyond our solar system, but its behavior. As telescopes around the world tracked its trajectory, they measured something extraordinary. This object was tumbling end over end with such extreme rotation that its brightness varied by a factor of 10. The light curve suggested an aspect ratio unlike anything in our solar system, perhaps 10 times longer than it was wide, like a cosmic cigar or needles spinning through space. But Oumuamua held another secret. As it rounded our sun and began its journey back into the void, sensitive measurements detected a small but real acceleration that could not be explained by gravity alone. Something was pushing this visitor away from our star, and we still do not know what. The most obvious explanation would be outgassing, the release of water vapor or other volatiles as the object heated up near the sun. This is what gives comets their characteristic tails and also provides a gentle rocket effect that can alter their orbits. But Oumuamua showed no visible coma, no tail, no obvious signs of sublimation at optical wavelengths. If it was outgassing, whatever it was releasing remained invisible to our instruments. Some researchers proposed exotic compositions, hydrogen ices that would sublimate without leaving detectable traces, or nitrogen ices similar to those found on Pluto's surface. Others suggested the object might be unusually porous, allowing volatiles to escape through internal channels without forming a visible coma. Each hypothesis carried its own problems and predictions that remained untested as Oumuamua faded into the darkness. The more sensational explanation that this might be artificial, perhaps a solar sail or probe from another civilization, captured public imagination, but failed to match the full data set. Solar radiation pressure alone could not account for the observed acceleration profile, and no radio signals were detected despite careful monitoring by SETI researchers. 2 years later, in August of 2019, another interstellar visitor arrived. This one, designated Tui Borisov, behaved exactly as astronomers expected an interstellar comet should behave. It sported a proper coma and tail, released familiar-looking dust and gas, and showed chemical signatures broadly similar to comets from our own solar system, with some intriguing differences in its carbon monoxide content. The Hubble Space Telescope and ground-based observatories tracked it for months, building a detailed portrait of what appeared to be a perfectly normal comet that simply happened to originate elsewhere. Borisov's conventional behavior made Oumuamua seem even more mysterious by comparison. Here we had two visitors from the same vast realm between the stars, yet they could hardly have appeared more different. One followed the rules we understood. The other broke them in ways that still perplex astronomers today. The third confirmed interstellar visitor finally arrived on July 1, 2025. The Atlas telescope in Chile spotted what would become 3 Atlas, designated the third known interstellar object to pass through our solar system. Unlike the previous false alarms that were later reclassified as solar system objects, this visitor's hyperbolic orbital path clearly indicated an origin from outside our solar system, confirmed by observations from multiple telescopes worldwide. 3 Atlas behaved like a proper comet, sporting a teardrop-shaped dust coma as captured by the Hubble Space Telescope. Spectroscopic observations revealed abundant water ice, both as solid grains and water vapor, along with a dust composition similar to organic-rich asteroids. This made it more similar to Tui Borisov than to the enigmatic Oumuamua, following expected patterns for an interstellar comet while carrying its own unique characteristics from whatever distant stellar system gave it birth. Beyond objects large enough to track with telescopes, we might also receive smaller visitors in the form of interstellar meteors. In 2014, a small object streaked through Earth's atmosphere above Papua New Guinea, creating a brilliant fireball that was detected by U.S. government sensors. Years later, a memo from U.S. Space Command suggested the object's measured velocity was accurate enough to indicate an interstellar trajectory, making it potentially the first confirmed interstellar meteor. But this claim remains contentious. Several astronomers have questioned whether the underlying sensor data, with its classified error bars and limited public documentation, truly supports such an extraordinary conclusion. The debate illustrates a fundamental challenge in studying these cosmic visitors. The most interesting objects are often the most difficult to confirm, and the evidence that reaches us is frequently incomplete or ambiguous. Some researchers have launched expeditions to search for microscopic spherules from the Papua New Guinea fireball, hoping to find physical remnants that might preserve isotopic signatures of interstellar origin. Others have conducted statistical analyses suggesting that interstellar meteors, if they exist, should be extremely rare compared to solar system debris. The question remains open, suspended between tantalizing possibility and the need for more definitive evidence. Even events from over a century ago continue to generate speculation about exotic visitors. The Tunguska event of 1908 flattened over 2,000 square kilometers of Siberian forest in what appears to have been a massive airburst. The scientific consensus points to a stony asteroid or comet that exploded perhaps 5 to 10 kilometers above the surface, releasing energy equivalent to hundreds of atomic bombs without leaving a traditional impact crater. Ongoing debates focus on the exact composition and structure of the impactor, but few mainstream researchers consider it anything other than a dramatic example of what can happen when our planet encounters a modest-sized space rock. These strange visitors from beyond our solar system remind us how little we know about the objects that drift through interstellar space. Each new detection teaches us something but also raises new questions. What kinds of processes create objects like Oumuamua? How many more await discovery? And what will the next interstellar visitor teach us about the cosmos beyond our sun's gravitational embrace? As we develop more sensitive surveys and better analytical techniques, we edge closer to answering these questions. But for now, Oumuamua continues its lonely journey into the void, carrying its secrets with it, while astronomers around the world scan the skies for the next mysterious messenger from the stars. Perhaps that visitor is already on its way, following a trajectory that will bring it within range of our telescopes in months or years to come. When it arrives, will it behave like the conventional Borisov, or will it perplex us in new ways we have yet to imagine? Cosmic wanderers' oddities. We have always assumed that if an object looks like an asteroid, it behaves like one, but the universe seems to enjoy confounding our expectations. In recent years, astronomers have identified a puzzling new class of objects they call dark comets, bodies that appear asteroid-like in our telescopes but exhibit the subtle orbital accelerations characteristic of comets. Unlike traditional comets, these objects show no visible tails or comas, no obvious signs of sublimating ice. Yet something is gently pushing them away from purely gravitational trajectories. The discovery emerged from careful analysis of asteroid orbits, where researchers noticed that some objects required small, persistent accelerations to match their observed positions. These accelerations followed the pattern expected from cometary outgassing, but the objects themselves remain stubbornly dark and tailless. Recent studies published in the Proceedings of the National Academy of Sciences have identified two distinct populations: inner dark comets that orbit closer to the Sun with faster rotations, and outer dark comets in the main asteroid belt that rotate more slowly. This finding matters for more than just celestial bookkeeping. Dark comets might represent a significant but previously unrecognized source of water and organic compounds throughout the inner solar system. If these objects are indeed releasing small amounts of water vapor or other volatiles in quantities too small to see but large enough to affect their orbits, they could help explain how Earth and other terrestrial planets acquired their water supplies. They also represent a potential impact hazard that current surveys might underestimate, since we typically assume asteroid-like objects follow predictable gravitational paths. Even stranger are the rogue planets, entire worlds that drift through interstellar space without any star to call home. Gravitational microlensing surveys, which detect these objects when they pass in front of more distant stars and briefly magnify their light, suggest that rogue planets might actually outnumber the planets that orbit stars. The galaxy could be teeming with dark, cold worlds drifting in permanent night. These planetary orphans likely form through two main processes. Some may be ejected from their birth systems during chaotic early epochs when young planets gravitationally scatter each other like billiard balls. Others might form in isolation from collapsing clouds of gas and dust never belonging to any star system. The largest of these rogue worlds could potentially retain substantial atmospheres heated by internal radioactive decay or tidal forces from unseen companions. Future telescopes like the James Webb Space Telescope and the planned extremely large telescopes on Earth might actually detect the faint thermal glow from some of these wandering worlds. If we find rogue planets with warm atmospheres maintained by internal heat sources, they could expand our concept of habitable environments beyond the traditional zones around stars. The search for evidence of advanced civilizations has also focused on cosmic wanderers of a different sort. Freeman Dyson proposed in 1960 that sufficiently advanced civilizations might construct vast swarms of solar collectors around their stars to capture and utilize stellar energy. These hypothetical Dyson spheres would absorb visible light and re-radiate it as infrared heat, creating a distinctive signature detectable across interstellar distances. Surveys using data from the Wide Field Infrared Survey Explorer and other infrared telescopes have searched for stars that appear unusually bright in infrared while remaining dim in visible light. The Glimpsing Heat from Alien Technologies survey has examined hundreds of thousands of galaxies, finding no evidence for galaxy-spanning Type 3 civilizations that have harnessed the energy output of entire stellar populations. A few individual stellar candidates have emerged from searches of Gaia and WISE data, but these require careful follow-up to distinguish genuine anomalies from instrumental artifacts or natural phenomena like unusual dust shells. The speculative nature of these searches cannot be overstated. We have no confirmed examples of alien technology, no template for how such megastructures might actually appear, and no guarantee that advanced civilizations would choose to build them at all. The searches continue primarily because the potential payoff confirmation that we are not alone would be so profound that even a small chance of success justifies the effort. More conventional cosmic wanderers include the many objects in our own solar system that appear to follow hyperbolic trajectories seemingly unbound from our sun's gravity. But appearances can deceive. Most objects with apparently hyperbolic orbits are actually long-period comets from the Oort cloud that have been gravitationally perturbed by the giant planets, particularly Jupiter. The perturbation can boost their velocities just enough to make them appear unbound when they are actually following extremely elongated elliptical paths. Distinguishing true interstellar objects from these hyperbolic pretenders requires extremely precise measurements of position and velocity, often over extended periods. This is one reason why confirmed interstellar visitors like Oumuamua and Borisov are so valuable. They represent unambiguous cases where we can be certain the object originated beyond our solar system. Even our studies of cosmic dust reveal wanderers from distant realms. Meteorites contain microscopic grains of materials that predate our solar system, preserving isotopic signatures from ancient stars that died billions of years before our sun was born. These pre-solar grains carry information about stellar nucleosynthesis, supernova explosions, and the chemical evolution of our galaxy. They are messengers from deep space and deep time embedded in rocks that fall from our own skies. Some interstellar dust produces puzzling spectroscopic features that we still do not fully understand. The 217.5 nanometer bump in the ultraviolet extinction curve of interstellar dust has been observed for decades, likely caused by carbonaceous grains, but the exact carrier remains uncertain. Such mysteries remind us that even the most basic components of interstellar space, the dust that drifts between stars, holds secrets we have yet to unlock. As we continue mapping the contents of our cosmic neighborhood and the spaces beyond, we discover that the universe is filled with wanderers, rogue planets, dark comets, ejected asteroids, ancient dust grains, and perhaps even the engineered artifacts of other civilizations. Each type of wanderer tells a different story about cosmic processes, from planetary formation to stellar death to the possible emergence of intelligence elsewhere in the galaxy. What unites all these cosmic wanderers is their ability to surprise us, to challenge our assumptions about how objects should behave and where they should be found. In a universe where rogue planets might outnumber ordinary planets and dark comets masquerade as asteroids, we are reminded that our understanding of even our local cosmic environment remains incomplete. The next wanderer we discover might be the most surprising yet: the power of black holes. We have always thought of black holes as exotic objects that take billions of years to grow to enormous size. But the James Webb Space Telescope keeps finding them where they should not exist. Within the first 500 to 700 million years after the Big Bang, when the universe was still a cosmic infant, JWST has detected supermassive black holes that already contain millions or billions of times the mass of our Sun. These monsters should not have had enough time to grow so large through conventional means. The puzzle has astronomers reconsidering fundamental assumptions about how black holes form and feed in the early universe. The standard picture suggests that the first black holes formed from the collapse of massive stars creating seed, black holes perhaps 10 to 100 times the mass of the Sun. These seeds would then grow by accreting surrounding gas and merging with other black holes. But even under optimal conditions, this growth process has limits. A black hole can only consume matter so quickly before the infalling material becomes hot and luminous enough to push away additional fuel through radiation pressure. This Eddington limit sets a speed limit on black hole growth. To reach supermassive proportions so early, these ancient black holes must have found ways around the usual constraints. Perhaps they formed through the direct collapse of massive primordial gas clouds, creating seeds that were already thousands of times more massive than stellar mass black holes. Or perhaps they grew through runaway mergers of massive stars in dense early clusters. Some models suggest they might have sustained super Eddington accretion rates growing faster than theory typically allows by swallowing matter through thick, obscuring envelopes that trapped radiation and prevented it from halting the feeding process. This remains an active frontier of research, with new observations from JWST continuing to refine our understanding of these early cosmic monsters. Each detection helps constrain the possible formation mechanisms and growth rates, gradually building a clearer picture of how supermassive black holes established themselves so early in cosmic history. Even in our local cosmic neighborhood, black holes exert influences that reach far beyond their immediate vicinity. Our own galaxy, along with thousands of others, flows through space toward a massive concentration of matter hidden behind the dusty plain of our Milky Way. This great attractor, located roughly 200 million light-years away, represents the gravitational center of our local group of galaxy clusters. Recent mapping efforts have revealed that we exist within a vast basin of gravitational attraction called Laniakea, a supercluster spanning 500 million light-years. The name means immeasurable heaven in Hawaiian, and it captures something essential about our cosmic address. We are not simply orbiting within our galaxy, but participating in flows of matter on scales so large they dwarf our everyday conception of space and motion. For a time, astronomers reported evidence of an even larger scale flow called dark flow, suggesting that galaxy clusters across vast regions of the observable universe were moving coherently in the same direction, as if pulled by some massive structure beyond our cosmic horizon. This would have represented a profound challenge to our standard cosmological model, which predicts that motions on such scales should be essentially random. However, subsequent analyses using data from the Planck satellite and other sources have found no robust evidence for this dark flow. The initial detections appear to have been artifacts of data analysis techniques or instrumental systematics. This represents an important lesson in how science progresses. Null results matter as much as positive detections, and extraordinary claims require extraordinary evidence that can withstand repeated scrutiny. While some black holes grow to enormous size and influence cosmic evolution on the largest scales, others remain surprisingly quiet. Sagittarius A. The supermassive black hole at the center of our own galaxy is remarkably underfed for an object containing over 4 million solar masses. Most of the time, it remains quiescent, producing only modest amounts of X-ray and radio emission as small amounts of gas trickle across its event horizon. Occasionally, Sagittarius A flares up as it encounters a particularly dense clump of material, or perhaps tears apart a passing star. These flares can increase its brightness by factors of hundreds or thousands for periods of hours or days, providing brief glimpses of the monster that lurks at our galaxy's heart. But for the most part, our central black hole appears to be on a starvation diet, consuming far less matter than it could theoretically accommodate. Other galaxies show evidence of black holes that have alternated between periods of vigorous feeding and relative quiet. The Hubble Space Telescope and Chandra X-ray Observatory have imaged spectacular bubbles and jets extending thousands of light-years from galactic centers, evidence of past episodes when central black holes consumed large quantities of matter and expelled vast amounts of energy. These outflows help regulate star formation throughout their host galaxies, creating a feedback loop that shapes galactic evolution over billions of years. Some astronomers have proposed that much smaller primordial black holes formed in the very early universe might account for some or all of the mysterious dark matter that appears to outweigh ordinary matter by factors of 5 to 1. These hypothetical objects would range in mass from microscopic to stellar proportions, having formed from extremely dense regions in the primordial universe rather than from the collapse of stars. Current constraints from gravitational lensing, gamma-ray observations, and other techniques have ruled out primordial black holes as the dominant component of dark matter across most mass ranges, but windows of possibility remain. The idea keeps returning because it offers a way to explain dark matter using physics we understand, rather than invoking exotic new particles that have so far eluded detection. At the extreme end of theoretical speculation lie objects like wormholes and white holes, which emerge naturally from the mathematics of general relativity but remain entirely hypothetical. Wormholes would represent tunnels through space-time connecting distant regions of the universe, while white holes would be the time-reversed opposites of black holes, spewing matter and energy rather than consuming it. The mathematics allows for such objects, but we have no idea how they might form in nature, or whether they could remain stable long enough to be observable. These exotic possibilities remind us that black holes, despite decades of study, continue to challenge our understanding of space-time and matter under the most extreme conditions. From the puzzling early growth of supermassive monsters to the quiet starvation of our local giant, from their role in shaping cosmic structure to their possible contribution to dark matter, black holes remain among the most powerful and mysterious objects in the universe. As our observational capabilities continue to improve, we edge closer to understanding how these remarkable objects form, grow, and influence their surroundings. But for now, they retain their ability to surprise us, to reveal new aspects of physics operating under conditions we cannot replicate on Earth, and to remind us that the universe contains phenomena that push the boundaries of our imagination. Cosmic structures too big to grasp. We have always assumed that matter in the universe is distributed more or less uniformly on the largest scales. But when we map the positions of galaxies across billions of light years, we find structures so immense, they challenge our models of how the universe evolved. The Boötes void stretches across 330 million light-years of space, a region so sparse in galaxies that it has earned the nickname the Great Nothing. If our Milky Way galaxy were located at its center, we would have discovered the existence of other galaxies only in the past few decades, so empty is this cosmic desert. Within a volume that should contain thousands of galaxies, we find fewer than 60. Voids like Boötes arise naturally from the way structure grows in an expanding universe. Regions that begin slightly less dense than average fall further behind as gravity pulls matter toward denser areas. Over billions of years, these underdense regions expand faster than the cosmic average, becoming increasingly empty as their meager contents get pulled toward the walls of surrounding galaxy clusters and filaments. But the sheer scale of the Boötes void pushes at the boundaries of what our standard cosmological model predicts should be possible. Computer simulations can produce voids this large, but they should be extremely rare. Finding one so close to our own cosmic neighborhood suggests either remarkable luck or gaps in our understanding of cosmic structure formation. Even more dramatic are the Great Walls of galaxies that span the observable universe. The Sloan Great Wall, one of the first such structures mapped by the Sloan Digital Sky Survey, extends across more than 1 billion light-years. It appears as a vast sheet of galaxies connected by filaments of dark matter, surrounding and defining enormous voids like bubbles in a cosmic foam. The significance of these structures depends partly on how we define them, and partly on the limitations of our surveys. When we look deeper into space, we see further back in time, so distant structures represent earlier epochs when the universe was smaller and denser. Comparing structures at different distances requires careful accounting for cosmic evolution and observational selection effects. Even more controversial is the Hercules Corona Borealis Great Wall identified through the clustering of gamma-ray bursts rather than galaxies themselves. If real, this structure would span more than 10 billion light-years, approaching the size of the observable universe itself. Such an enormous structure would challenge fundamental assumptions about cosmic homogeneity and the maximum size that gravitational collapse could produce. The statistical significance of this claimed structure remains debated. Gamma-ray bursts are relatively rare events, and finding patterns in their distribution requires careful statistical analysis to distinguish genuine clustering from chance alignments. Different analysis techniques yield different conclusions about whether the structure is real or simply a statistical fluctuation in a limited dataset. Similar controversies surround other claimed megastructures, including alignments of quasar polarization axes across billions of light-years. If confirmed, such alignments would suggest coherent magnetic fields or other organizing principles operating on scales far larger than current theory predicts. But the observations push at the limits of what our instruments can reliably measure, and alternative explanations invoking selection effects or systematic errors remain plausible. One structure that appears more solidly established is the cold spot in the cosmic microwave background radiation, a region roughly 20 degrees across, where the ancient light from the Big Bang appears slightly cooler than average. This temperature difference amounts to only a few dozen microkelvin, but it represents a significant deviation from the otherwise remarkably uniform background radiation. The cold spot might be linked to a supervoid in the foreground, a region of space containing fewer galaxies than average. As cosmic microwave background photons travel through such an underdense region, they lose energy through a process called the integrated Sachs-Wolf effect, arriving at Earth slightly cooler than they would have otherwise. However, the magnitude of the observed temperature deficit appears larger than this effect alone can easily explain. Alternative explanations for the cold spot range from exotic physics in the early universe to statistical flukes in the cosmic microwave background patterns. Some researchers have suggested it might represent a collision between our universe and another in a multiverse scenario, though such ideas remain highly speculative and difficult to test. More conventional but equally impressive are the dark matter filaments that connect galaxy clusters across hundreds of millions of light-years. These cosmic web structures are largely invisible to ordinary telescopes, since they consist primarily of dark matter and hot gas. But their gravitational effects can be detected through weak lensing, the subtle distortion they impose on the shapes of background galaxies. Recent observations have successfully mapped several of these filaments, revealing the skeletal structure of the cosmic web that theory has long predicted. These observations represent remarkable technical achievements requiring exquisite control of systematic errors and sophisticated statistical analysis to extract faint signals from noisy data. The discovery that our universe is accelerating its expansion, driven by the mysterious dark energy that comprises roughly 70% of the cosmic energy budget, has profound implications for the future of these large-scale structures. If the acceleration continues, eventually even nearby galaxy clusters will be carried apart by expanding space, leaving our local group increasingly isolated in an ever-emptying universe. Current observations from Type Ia supernovae, which led to the 1998 discovery of cosmic acceleration, continue to be refined with larger samples and better understanding of systematic errors. The Dark Energy Spectroscopic Instrument and other ongoing surveys are mapping the expansion history of the universe in unprecedented detail, searching for clues about the nature of whatever is driving the acceleration. As we continue mapping the universe on ever larger scales, we find structures that test the limits of our theoretical understanding. From vast voids that seem too empty to great walls that seem too long, from mysterious cold spots to invisible filaments of dark matter, the large-scale universe continues to surprise us with its complexity and grandeur. These observations force us to confront fundamental questions about the nature of space-time and matter on the largest possible scales. They remind us that even our most successful cosmological models may be incomplete, missing ingredients or processes that operated in the early universe or continue to shape cosmic evolution today. Perhaps most remarkably, all of these immense structures emerged from tiny quantum fluctuations in the very early universe, variations in density that were stretched and amplified by cosmic inflation into the seeds of everything we observe today. In mapping these structures, we are reading the fossil record of creation itself, deciphering clues about processes that occurred when our universe was a fraction of a second old. Missing pieces of the universe. We have always counted the matter we can see and assumed we were accounting for most of what exists. But the universe appears to be playing an elaborate shell game with the majority of its contents. For decades, astronomers faced an embarrassing problem. They could account for less than half of the ordinary matter that should exist, based on measurements of primordial nucleosynthesis in the early universe. The missing baryons, protons, and neutrons that make up normal atoms seem to have vanished without a trace. Stars, galaxies, and even the diffuse gas between galaxies added up to far less than theoretical predictions demanded. The solution came from an unexpected source: fast radio bursts, those millisecond flashes of radio waves from distant galaxies. As these signals travel across billions of light years, they encounter free electrons in the thin plasma that fills intergalactic space. The electrons cause different radio frequencies to arrive at slightly different times, an effect called dispersion that allows astronomers to measure the total amount of free electrons along the line of sight. These measurements revealed that much of the missing ordinary matter exists as a warm, hot intergalactic medium, a tenuous plasma heated to millions of degrees and spread throughout the cosmic web. This material is too hot to emit visible light, but too cool to shine brightly in X-rays, making it nearly invisible until fast radio bursts provided a new way to detect it. The discovery represents a triumph of creative astronomy, using exotic cosmic phenomena to solve a fundamental accounting problem. But the mystery of missing matter pales beside the enigma of dark matter itself, which outweighs ordinary matter by roughly 5-to-1, yet interacts only through gravity. Decades of increasingly sensitive experiments have failed to directly detect dark matter particles, despite theoretical predictions that they should occasionally collide with atomic nuclei in underground detectors. The leading candidates include weakly interacting massive particles, or WIMPs, that would have been produced in the early universe and survived until today. Alternative possibilities include actions, hypothetical particles originally proposed to solve problems in the theory of the strong nuclear force, or sterile neutrinos, that interact even more weakly than ordinary neutrinos. Each possibility makes different predictions for how dark matter should behave and what kinds of signals it might produce. Some researchers have proposed that dark matter might not consist of particles at all, but rather represents a modification of gravity itself on large scales. These modified gravity theories can explain many observations of galactic rotation curves and galaxy cluster dynamics without invoking invisible matter, though they face challenges in explaining the full range of dark matter evidence, particularly the behavior of colliding galaxy clusters. Even more mysterious is dark energy, the unknown force that appears to be accelerating the expansion of the universe. Unlike dark matter, which clumps gravitationally and helps build cosmic structure, dark energy appears to be smoothly distributed throughout space and to have remained roughly constant in density even as the universe expanded. This implies that space itself is creating more dark energy as it grows, a violation of conventional energy conservation that points toward profound gaps in our understanding of fundamental physics. The simplest explanation for dark energy is Einstein's cosmological constant, a form of energy inherent in empty space itself. But when physicists try to calculate how much vacuum energy quantum mechanics predicts they get, answers that are larger than observations allow by factors of 10 to the 60th power, or even 10 to the 120th power. This vacuum energy problem represents perhaps the worst prediction in the history of physics, suggesting fundamental flaws in how we understand the relationship between quantum mechanics and gravity. Alternative models for dark energy include quintessence, a slowly rolling scalar field similar to the one thought to drive cosmic inflation, or phantom energy, which would have the bizarre property of becoming denser as the universe expands. If dark energy is phantom energy, it would eventually accelerate the expansion so much that even atoms would be torn apart in a big rip scenario. Recent observations from the Dark Energy Spectroscopic Instrument have provided hints that dark energy might not be perfectly constant after all, but these preliminary results require confirmation from additional data and analysis. If confirmed, evidence for evolving dark energy would revolutionize cosmology and provide new clues about the nature of whatever is driving the acceleration. The shape of space itself remains another fundamental mystery. Current observations from the Planck satellite and other sources indicate that the universe is geometrically flat to within about 1%, meaning that parallel lines remain parallel over cosmic distances, and the angles of triangles add up to exactly 180 degrees. But this flatness requires an extraordinary fine-tuning of the total matter and energy density, leading many cosmologists to invoke cosmic inflation as the mechanism that flattens space in the very early universe. If the universe is not perfectly flat, it could either be slightly curved like the surface of a sphere, in which case it would eventually stop expanding and collapse back on itself, or curved like a saddle, in which case it would expand forever at an ever-accelerating rate. Current observations cannot definitively distinguish between these possibilities, leaving open fundamental questions about the ultimate fate of everything we know. These mysteries of missing matter, dark energy, and cosmic geometry point toward a deeper puzzle about the nature of reality itself. Some physicists have proposed that our observable universe is just one of countless others in a vast multiverse where different regions have different physical laws and constants. In such a scenario, we would find ourselves in a universe suitable for complex chemistry and biology, simply because we could not exist in regions with different properties. The multiverse idea remains highly speculative and notoriously difficult to test, since by definition we cannot observe other universes directly. Critics argue that unfalsifiable theories stretch the boundaries of science into philosophy or even theology. Proponents counter that the multiverse represents a natural consequence of our best theories of fundamental physics and cosmology, particularly eternal inflation models that predict the continuous creation of new cosmic regions with randomly varying properties. Meanwhile, more conventional approaches focus on mapping what we can observe in our own universe with ever greater precision. The cosmic web of dark matter filaments, the distribution of galaxies across billions of light years, and the subtle patterns in the cosmic microwave background radiation all carry information about the fundamental physics that shaped cosmic evolution. As our observations become more precise and our theoretical understanding deepens, we inch closer to solving some of these cosmic puzzles. But each answer seems to reveal new questions, new layers of mystery that remind us how much we still do not know about the universe we inhabit. The missing pieces may be invisible, but their influence shapes everything we see, from the motion of stars in distant galaxies to the ultimate fate of space and time itself. Mysterious stars. We have always thought we understood the basic life cycle of stars, from birth and collapsing gas clouds to death as white dwarfs, neutron stars, or black holes. But the James Webb Space Telescope has been finding stellar explosions in the early universe that challenge our timeline of cosmic evolution. These ancient supernovae, detected when the universe was less than 1 billion years old, suggest that massive stars were forming, living and dying much earlier than many models predicted. The first generation of stars, known as population 3 stars, should have been composed almost entirely of hydrogen and helium, lacking the heavier elements needed to cool gas clouds efficiently and form lower-mass stars like our Sun. According to theory, these primordial stars should have been extremely massive, perhaps hundreds of times heavier than the Sun, and correspondingly short-lived. When they exhausted their nuclear fuel after only a few million years, they should have exploded as pair instability supernovae, completely destroying themselves while dispersing the first heavy elements into space. These explosions would have been among the most powerful events in cosmic history, briefly outshining entire galaxies. The supernovae that JWST observes at high redshift might represent this first generation of stellar deaths, providing our first direct glimpse of how the universe began manufacturing elements heavier than hydrogen and helium. Each detection helps refine our understanding of when and how the first stars formed, how massive they were, and how their explosions enriched the primordial cosmos with the ingredients necessary for planets and life. Even in our local cosmic neighborhood, some stars behave in ways that perplex astronomers. Magnetars represent perhaps the most extreme stellar remnants in the known universe. Neutron stars with magnetic fields, trillions of times stronger than Earth's, so powerful they can strip electrons from atoms at distances of thousands of kilometers and twist space-time itself into exotic configurations. In December of 2004, the magnetar SGR 180620 unleashed a flare so powerful it briefly saturated X-ray detectors across the solar system. The explosion released more energy in 1/10 of a second than our Sun produces in 100,000 years, and its effects were detected as far away as Mars. Had this event occurred at the distance of our nearest stellar neighbor, it would have triggered a mass extinction on Earth. Such monster flares occur when the magnetar's crust cracks under the enormous stress of its twisted magnetic field, suddenly releasing vast amounts of stored magnetic energy. These events help explain the connection between magnetars and fast radio bursts, those mysterious millisecond flashes that can briefly outshine all the stars in a galaxy. The 2020 detection of a fast radio burst-like emission from SGR 1935 plus 2154 provided the first direct link between these phenomena. Other stellar explosions tell different stories about the violent ends of massive stars. Gamma-ray bursts represent the most powerful explosions in the universe since the Big Bang, releasing more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. Long-duration gamma-ray bursts appear to mark the collapse of extremely massive stars into black holes, while short bursts likely result from the collision and merger of neutron stars. These cosmic lighthouses can be detected across billions of light-years, making them valuable probes of star formation and stellar death throughout cosmic history. Their intense radiation illuminates and ionizes gas clouds across vast distances, and their heavy element production through rapid neutron capture helps explain the abundance of gold, platinum, and other precious metals in the universe. Not all neutron stars announce themselves through violent explosions. Pulsars, rotating neutron stars that sweep beams of radiation across space like cosmic lighthouses, provide some of the most precise natural clocks in the universe. Their rotation periods can be measured to 15 decimal places, making them sensitive to gravitational waves, changes in Earth's rotation, and even the motion of our solar system through the galaxy. Arrays of pulsars scattered across the sky now serve as a galaxy-spanning gravitational wave detector sensitive to the slow ripples in space-time produced by orbiting supermassive black holes in distant galaxies. These pulsar timing arrays complement ground-based detectors like LIGO and Virgo, opening a new window on gravitational wave astronomy that extends to much larger scales and longer time scales. Some stellar remnants occupy theoretical territory so exotic they challenge our understanding of what kinds of objects can exist. Thorne-Jitkov objects would represent red supergiant stars, with neutron star cores, hybrid monsters created when a neutron star spirals into and merges with a normal star. The neutron star would continue burning nuclear fuel in the envelope around it, creating a star powered by processes unlike anything else in the universe. Astronomers thought they had identified such an object in HV 2112, a red supergiant in the small Magellanic Cloud with unusual chemical signatures suggesting neutron star nucleosynthesis. However, subsequent observations raised questions about this identification, illustrating how difficult it can be to confirm the existence of theoretical objects that exist at the boundaries of stellar physics. Even more speculative are the predictions that occasionally surface, claiming astronomers can forecast stellar explosions years in advance. In 2020, some researchers predicted that the contact binary system KIC 9832227 would merge and explode as a red nova in 2022 based on apparent period changes that seemed to follow the same pattern observed before the 2008 red nova in Scorpius. The predicted explosion never occurred. More careful analysis revealed that the apparent period changes were likely artifacts of data analysis techniques rather than genuine orbital decay. The retraction of this prediction serves as a reminder that astronomy, like all sciences, works through a process of hypothesis testing and correction. Even experienced researchers can be misled by subtle instrumental effects or statistical coincidences that initially appear significant. This episode illustrates the importance of skepticism and peer review in astronomy. Extraordinary claims about predictable stellar explosions naturally attract attention, but they also require extraordinary evidence that can withstand careful scrutiny. The willingness to acknowledge and correct errors when new evidence emerges represents one of the fundamental strengths of the scientific process. Meanwhile, genuine mysteries continue to emerge from our ongoing stellar surveys. Stars that appear to violate the basic rules of stellar evolution, stars that exist in configurations theory suggests should be unstable, and stars that simply vanish without explanation, all remind us that the universe retains the capacity to surprise us. Each new mystery adds another piece to the complex puzzle of how stars form, evolve, and die throughout cosmic history. From the exotic physics of magnetars to the theoretical possibilities of hybrid objects, from the predictable precision of pulsars to the unpredictable nature of stellar explosions, stars continue to reveal new aspects of matter and energy operating under the most extreme conditions nature can provide. As our observational capabilities improve and our theoretical understanding deepens, we edge closer to solving some of these stellar puzzles. But stars, those fundamental building blocks of cosmic structure and stellar nucleosynthesis, retain their ability to challenge our assumptions and remind us that even the most familiar objects in the universe can harbor profound mysteries. The next stellar discovery might reveal phenomena we have never imagined, pushing our understanding of physics into entirely new territory: vanishing and impossible stars. We have always assumed that massive stars die in spectacular supernova explosions, broadcasting their death throes across billions of light years. But some stars seem to prefer more discreet exits from the cosmic stage. The search for the universe's first stars, the massive population 3 objects that should have formed from primordial hydrogen and helium, continues to come up empty despite increasingly powerful telescopes and sophisticated search strategies. These metal-free giants should have been fundamentally different from modern stars, perhaps hundreds of times more massive than our Sun and correspondingly luminous. When they died, they should have exploded as pair instability supernovae, completely annihilating themselves while dispersing the first heavy elements into space. These explosions would have been among the most powerful events in cosmic history, briefly outshining entire galaxies. Yet despite decades of searching, astronomers have found no convincing examples of active population 3 stars. The James Webb Space Telescope has detected some candidate signatures of these primordial objects, including unusually hot metal-poor stars in the early universe, but definitive identification remains elusive. Part of the challenge lies in distinguishing genuine population 3 stars from extremely metal-poor population 2 stars that formed shortly afterward, when the first heavy elements were already present in tiny quantities. The continued absence of confirmed population 3 stars raises questions about our models of early star formation. Perhaps these primordial giants were rarer than predicted, or perhaps they existed only briefly in isolated pockets of the early universe. Alternatively, they might be hiding in plain sight, disguised by subsequent enrichment from nearby star formation, or detectable only through indirect signatures we have not yet learned to recognize. Other stars achieve a kind of immortality through violence, stealing mass and youth from their companions in binary systems. Blue stragglers appear far too hot and massive for their age, as if they have somehow reversed the aging process that should have left them as cool, dim red stars by now. These stellar fountains of youth likely acquire their rejuvenated appearance through mass transfer from companion stars or through direct collisions and mergers in dense stellar environments. The process of creating a blue straggler involves either stripping material from a companion star through gravitational tides or merging completely with another star in a cosmic collision. Either scenario can provide fresh hydrogen fuel to restart nuclear burning in the core, effectively resetting the stellar evolution clock and giving the star a second lease on life. The result is a star that appears younger and more massive than it actually is, a stellar imposter masquerading among genuinely young stars. At the other extreme are hypervelocity stars, objects moving so fast through space that they will eventually escape our galaxy entirely. These stellar refugees achieve their enormous speeds through gravitational slingshot encounters with the supermassive black hole at the center of our galaxy, a process known as the Hills mechanism. When a binary star system wanders too close to Sagittarius A, tidal forces can tear the pair apart, sending one star plunging into the black hole while flinging the other outward at speeds of thousands of kilometers per second. Most hypervelocity stars are hot, massive objects that likely originated in the galactic center before their violent ejection. But surveys have also found examples of lower mass stars with high velocities, suggesting alternative ejection mechanisms involving interactions with intermediate mass black holes or supernova explosions in binary systems. Each hypervelocity star carries information about the extreme environments where it achieved its remarkable speed. Some stars reveal their internal structure through the stellar equivalent of earthquakes. Starquakes occur when neutron stars suddenly readjust their crusts under the enormous stress of rotation and magnetic fields, releasing bursts of X-rays and gamma rays detectable across interstellar distances. But even normal stars experience seismic activity that creates subtle oscillations detectable through precise photometry. Asteroseismology, the study of stellar oscillations, allows astronomers to probe the internal structure of stars with remarkable precision. The Kepler Space Telescope and its successor TESS have detected oscillations in thousands of stars, revealing details about their core composition, rotation rates, and evolutionary status that would be impossible to determine through conventional observations. These stellar seismic waves travel through stellar interiors at different speeds depending on temperature, density, and composition, creating an acoustic fingerprint that reveals the star's internal architecture. The precision of astroseismic measurements allows astronomers to determine stellar ages with uncertainties of just a few percent, providing crucial constraints on galactic evolution and the history of planet formation. By studying stars similar to our Sun, but at different evolutionary stages, we can glimpse our own star's past and future with unprecedented clarity. Perhaps most mysterious are the stars that simply disappear without explanation. N6946 BH1 was a red supergiant star in a nearby galaxy that suddenly vanished from visible light observations while continuing to emit infrared radiation. This behavior suggests the star collapsed directly into a black hole, without producing a visible supernova explosion, a scenario theoretical models predict should occasionally occur for the most massive stars. Such failed supernovae represent a fundamentally different mode of stellar death, where the core collapse proceeds so rapidly that the shockwave cannot escape, and the entire star simply vanishes behind an event horizon. These events would produce far less visible light than conventional supernovae, but might generate detectable gravitational waves as matter falls into the newly formed black hole. Other vanishing stars may represent supernova imposters, luminous blue variable stars that undergo massive eruptions resembling supernovae but survive the experience. Objects like SN2008S and SN2009IP initially appeared to be genuine supernovae but later showed signs of ongoing activity suggesting the original star had survived its apparent death. These events likely involve the ejection of massive stellar envelopes through instabilities in the final stages of stellar evolution. The study of vanishing and impossible stars pushes our understanding of stellar physics into uncharted territory. Each disappearance, each apparent violation of stellar evolution theory, each object that exists where it should not, or behaves in ways we do not expect, adds new complexity to our picture of how stars form, live, and die. As our surveys become more comprehensive and our theoretical models more sophisticated, we continue to discover stellar phenomena that challenge our assumptions. The universe seems to delight in creating stars that exist at the boundaries of possibility, objects that test the limits of stellar physics and remind us that nature is often more creative than our theories anticipate. These stellar mysteries also remind us that our galaxy is a dynamic, evolving system where stars are constantly being born, living their lives, and meeting their fates in ways both familiar and exotic. Each vanishing star, each impossible object, each stellar refugee fleeing our galaxy at hypervelocity speeds tells a story about processes we are still learning to understand. In studying these cosmic outliers, we glimpse the full range of stellar behavior and the remarkable diversity of ways that matter and energy can organize themselves under the extreme conditions found in stellar interiors. Solar system puzzles. We have always assumed that our solar system formed through orderly processes with planets accreting from a smooth disk of gas and dust around the young sun. But nearly every world we have studied closely reveals a history far more chaotic and puzzling than this simple picture suggests. Earth itself presents one of the most fundamental puzzles in planetary science. How did our world remain warm enough for liquid water when the young sun was about 30% dimmer than it is today? This faint young sun paradox suggests that early Earth should have been a frozen snowball with temperatures well below the freezing point of water. Yet geological evidence clearly shows that liquid water existed on Earth's surface as early as 4 billion years ago, perhaps even earlier. The most likely solutions involve atmospheric compositions very different from today's. Early Earth may have possessed a much thicker atmosphere rich in greenhouse gases like carbon dioxide, methane, or ammonia. These molecules would have trapped solar radiation more efficiently than the current atmosphere, compensating for the sun's lower luminosity. Alternatively, different cloud compositions or albedo effects might have allowed Earth to retain more heat than simple models predict. The puzzle becomes more complex when we consider that too much atmospheric greenhouse warming would have triggered a runaway effect, transforming Earth into a Venus-like hell world with surface temperatures hot enough to melt lead. The fact that Earth avoided this fate while maintaining liquid water suggests a delicate balance of processes that we still do not fully understand. Venus itself raises related questions about planetary evolution and the boundaries of habitability. Some climate models suggest that Venus could have maintained temperate surface conditions for billions of years, if it rotated more rapidly in its youth, allowing for the formation and persistence of water oceans. Other models argue that Venus was likely hot and dry from very early in its history due to its proximity to the Sun and the physics of atmospheric water loss. In this scenario, any water Venus might have possessed early in its history would have been rapidly lost to space through photodissociation and hydrogen escape, leaving the planet dry long before complex atmospheric evolution could occur. The debate matters for our understanding of potentially habitable exoplanets. If Venus represents a world that was once Earth-like but succumbed to a runaway greenhouse effect, it serves as a cautionary tale about the fragility of planetary habitability. If Venus was never habitable, then Earth-like conditions may be even rarer than we currently believe. Mars presents its own atmospheric puzzle. The red planet clearly had a thicker atmosphere in its ancient past, as evidenced by networks of valleys that appear carved by flowing water and mineral deposits that could only have formed in the presence of liquid water. But Mars lost most of this early atmosphere through a process we are only beginning to understand. The MAVEN spacecraft has measured the ongoing escape of Mars's thin atmosphere, showing how solar wind particles strip away atmospheric gases at a rate of about 250 grams per second. Over billions of years, this gentle hemorrhaging could account for the loss of a substantial atmosphere. The process accelerated during solar storms when the enhanced solar wind removed atmospheric gases at rates hundreds of times higher than average. This atmospheric erosion was likely much more severe early in Mars's history when the young sun produced stronger stellar winds and more frequent magnetic storms. Without the protection of a strong global magnetic field, like Earth's, Mars was defensively exposed to these atmospheric assaults. The loss of its atmosphere triggered a cascade of changes that transformed Mars from a potentially habitable world into the cold, dry planet we see today. In the outer solar system, giant planets display their own peculiar characteristics that challenge our understanding of planetary formation and evolution. Saturn's hexagonal storm at its north pole represents one of the most geometrically perfect features found anywhere in nature, a six-sided jet stream that has persisted for decades. Laboratory experiments using rotating tanks of fluid can reproduce similar polygonal patterns, suggesting that Saturn's hexagon results from the interaction between different wind speeds at different latitudes. Neptune emits more than twice as much energy as it receives from the Sun, indicating a substantial internal heat source that has persisted for over 4 billion years. This excess heat likely represents energy left over from the planet's formation, when gravitational contraction and the decay of radioactive elements heated the interior to thousands of degrees. The fact that Neptune still retains this primordial heat suggests that giant planet interiors cool much more slowly than simple models predict. Uranus presents perhaps the strangest case among the giant planets, rotating on its side with an axial tilt of 98 degrees. This extreme orientation almost certainly results from a catastrophic collision early in the solar system's history, when a Mars-sized object struck Uranus with enough force to knock it over. Alternative scenarios involving multiple smaller impacts or gravitational interactions with migrating planets remain possible, but a single giant impact provides the simplest explanation for Uranus's unusual properties. Jupiter's Great Red Spot has raged for at least 3 centuries, possibly much longer, making it one of the most persistent weather systems in the solar system. This enormous anticyclonic storm is large enough to swallow Earth whole, yet it has been gradually shrinking over the past century for reasons that remain unclear. The Juno spacecraft has provided new insights into the storm's depth and structure, showing that it extends hundreds of kilometers below the visible cloud tops, but the source of its longevity remains mysterious. Even more puzzling is the hypothetical Planet 9, a proposed super-Earth that might orbit in the distant reaches of our solar system. Statistical analysis of the orbits of trans-Neptunian objects suggests that their paths are influenced by the gravity of an unseen world, perhaps 5 to 10 times more massive than Earth. However, observational bias could also explain the apparent clustering, making it difficult to distinguish between genuine gravitational shepherding and the effects of incomplete surveys. The search for Planet 9 continues with increasingly sensitive telescopes and sophisticated analysis techniques. If it exists, this distant world would represent a fundamentally different class of planet from anything else in our solar system, a super-Earth similar to the most common type of exoplanet but somehow stranded in our system's outer reaches. Perhaps most mysterious of all is the Oort cloud, the vast spherical shell of comets that theoretically surrounds our solar system at distances of thousands of astronomical units. Despite strong theoretical reasons to believe it exists, and statistical evidence from comet orbits that supports its presence, no telescope has ever directly imaged the Oort cloud or detected individual objects within it, except when they fall inward to become visible comets. This ghostly reservoir of primordial ice represents one of the largest structures associated with our solar system, potentially containing trillions of comets left over from the solar system's formation. Its very existence depends on theoretical models and indirect evidence, making it simultaneously one of our most confident predictions and one of our most elusive confirmations. These solar system puzzles remind us that even our local cosmic neighborhood, the planetary system we call home, retains profound mysteries. From atmospheric paradoxes to vanishing storms to invisible comet reservoirs, our solar system continues to surprise and perplex us. Each new mission and observation reveals additional complexity, additional questions that challenge our understanding of how planetary systems form and evolve over billions of years. Planets and moons that surprise us. We have always pictured the outer solar system as an orderly realm of predictable orbits and ancient, unchanging worlds. But recent discoveries reveal a collection of moons and small bodies that harbor more activity and mystery than we ever imagined possible. The Kuiper Belt, that disk of icy remnants beyond Neptune's orbit, displays several features that our models of solar system formation struggle to explain. The so-called Kuiper Cliff marks a sharp drop-off in the number of objects beyond about 50 astronomical units from the Sun, as if some process swept the outer regions nearly clean of debris. Gravitational interactions with Neptune can explain some of this structure, but the cliff appears sharper than simulations typically produce. Even stranger are the detached objects like Sedna, which orbit so far from the Sun that Neptune's gravity cannot account for its current trajectory. Sedna's closest approach to the Sun lies well beyond Neptune's influence, yet something must have lifted it into such a distant orbit. Possible explanations include a passing star that gravitationally scattered objects in the early solar system, or perhaps the influence of the hypothetical planet 9. But no single mechanism easily explains all the observed orbital peculiarities. These distant worlds carry information about the solar system's earliest epoch, when planets were still migrating and gravitational interactions were reshaping the architecture of planetary orbits. Each unusual trajectory preserves evidence of ancient dynamical processes that may have been crucial in determining why our solar system has the configuration we observe today. Mars continues to puzzle us with evidence for dramatic changes in its climate history. The planet clearly had flowing water on its surface billions of years ago, as evidenced by ancient river valleys, lake beds, and mineral deposits that require liquid water to form. But the transition from this ancient wetter Mars to the cold, dry world we see today remains poorly understood. The MAVEN mission has shown us how Mars continues to lose its atmosphere to space even today, with solar wind particles stripping away atmospheric gases at measurable rates. During solar storms, this atmospheric escape accelerates dramatically, suggesting that the young sun's more vigorous activity could have stripped away a substantial atmosphere over geological time. But atmospheric escape alone may not fully account for Mars's transformation. Some of the planet's early atmosphere might be locked away in carbonate rocks or other mineral deposits hidden beneath the surface where our current instruments cannot detect it. Alternative scenarios suggest that Mars's early atmosphere was never thick enough to support a warm, wet climate, and that liquid water existed only during brief periods of volcanic heating or asteroid impacts. In our ongoing search for signs of life, one of the most intriguing episodes involved the claimed detection of phosphine in Venus's atmosphere in 2020. Phosphine, a molecule consisting of phosphorus and hydrogen, has no known abiotic source in Venus's oxidizing atmosphere, making it a potential biosignature if the detection proved correct. However, subsequent reanalysis of the same data and independent observations with the ALMA radio telescope array have failed to confirm the phosphine detection. The initial signal appears to have been an instrumental artifact or a misidentification of sulfur dioxide, a common component of Venus's atmosphere. This episode illustrates how extraordinary claims require extraordinary evidence, and how the scientific process of peer review and independent verification helps distinguish genuine discoveries from spurious signals. The debate over Venusian phosphine also highlighted how little we know about the complex chemistry of planetary atmospheres under extreme conditions. Venus's surface temperature of over 450 degrees Celsius and crushing atmospheric pressure create an environment unlike anywhere else in the solar system, where chemical reactions might proceed through pathways we have never studied in laboratory settings. Jupiter's moon. Europa has emerged as one of the most promising places to search for life beyond Earth. The Galileo spacecraft's magnetometer detected signatures consistent with a global ocean of liquid water beneath Europa's icy crust, maintained by tidal heating from Jupiter's powerful gravity. This hidden ocean likely contains more water than all of Earth's oceans combined, and it has persisted for billions of years in an environment protected from space radiation by kilometers of overlying ice. Recent observations have detected what appear to be water vapor plumes erupting from Europa's surface, possibly providing direct access to the subsurface ocean without the need to drill through the ice shell. These plumes, if confirmed, could allow future missions to sample Europa's ocean by simply flying through the ejected material searching for organic compounds or other signs of biological activity. Saturn's small moon Enceladus provides an even more dramatic example of subsurface ocean activity. The Cassini spacecraft flew directly through geysers of water vapor and organic compounds erupting from Enceladus's south polar region, analyzing the composition of material ejected from a subsurface ocean. These measurements revealed not only water and simple organic compounds, but also complex molecules and even phosphorus, a crucial element for life as we know it. The discovery of phosphorus in Enceladus's plumes was particularly significant because this element is often considered a limiting factor for biological activity. All known life requires phosphorus for DNA, RNA, and energy storage molecules like ATP. Finding phosphorus in Enceladus's ocean suggests that this tiny moon possesses the basic chemical ingredients necessary for life, at least in principle. Saturn's largest moon, Titan, presents yet another intriguing possibility for exotic forms of life. Titan's thick atmosphere and surface lakes of liquid methane and ethane create conditions unlike anywhere else in the solar system. While these temperatures are far too cold for water-based life, some scientists have speculated about alternative biochemistries that might operate in Titan's hydrocarbon-rich environment. The Cassini mission's radar mapping of Titan revealed a complete hydrological cycle involving methane instead of water, with methane rain rivers, lakes, and seas shaping the moon's surface. This alien water cycle operates under physical principles similar to Earth's weather systems, but uses entirely different chemistry, creating landscapes that are simultaneously familiar and alien. These discoveries of active, potentially habitable worlds throughout our solar system have revolutionized our understanding of where life might exist. The traditional concept of a habitable zone around stars where temperatures allow liquid water to exist on planetary surfaces has expanded to include the possibility of subsurface oceans maintained by tidal heating, radioactive decay, or other energy sources. Ocean worlds like Europa and Enceladus, and possibly even distant Pluto, may represent the most common type of potentially habitable environment in our solar system and throughout the universe. If life can thrive in these hidden oceans, then the number of potentially inhabited worlds in our galaxy might be orders of magnitude larger than estimates based solely on planets in the traditional habitable zones around their stars. Ocean worlds could exist around virtually any star regardless of the distance that would make surface water impossible. Each new mission to these mysterious worlds reveals additional complexity and raises new questions about the conditions necessary for life. As we continue exploring our solar system's moons and small bodies, we discover that the boundary between living and non-living worlds may be far more blurred than we once believed. The next great discovery in astrobiology might come not from a distant exoplanet, but from one of these surprising worlds in our own cosmic backyard. Alien life. The Great Silence. We have always wondered whether we are alone in the universe yet. After decades of searching, the cosmos remains stubbornly silent. This absence of detectable alien civilizations, despite the vast number of potentially habitable worlds, creates one of the most profound puzzles in all of science. The Fermi paradox, named after physicist Enrico Fermi's famous lunchtime question in 1950, crystallizes this mystery in simple terms. If the galaxy contains billions of stars, many with planets that could support life, and if life had billions of years to evolve and spread throughout the galaxy, then where is everybody? The numbers seem to suggest that we should be surrounded by evidence of alien civilizations, yet we detect nothing. Various solutions to this paradox have been proposed, each carrying profound implications for our understanding of life intelligence and our place in the cosmos. Perhaps life itself is extraordinarily rare, arising only under very specific conditions that few planets can provide. Alternatively, perhaps life is common, but intelligence is rare, requiring unlikely evolutionary pathways that most biospheres never achieve. More sobering possibilities involve great filters, catastrophic events, or fundamental limitations that prevent most civilizations from reaching a level of technological development where they become detectable across interstellar distances. These filters might operate at various stages of development, preventing the origin of life, blocking the evolution of complex cells, hindering the development of intelligence, or causing technological civilizations to destroy themselves before they can spread beyond their home worlds. If the great filter lies in our past, then we represent an extraordinarily unlikely success story, having somehow overcome barriers that stop most other potential civilizations. If the filter lies in our future, then advanced civilizations may inevitably encounter challenges that lead to their extinction or withdrawal from observable activity. One speculative resolution to Fermi's paradox is the zoo hypothesis, first proposed by John Ball in 1973. This idea suggests that advanced alien civilizations are indeed aware of us, but have chosen not to make contact, perhaps treating our solar system as a kind of nature preserve, or maintaining some form of galactic quarantine protocol. The zoo hypothesis faces obvious challenges in terms of testability and the coordination it would require among multiple alien civilizations. It also raises uncomfortable questions about human agency and the possibility that our apparent freedom to explore and expand might exist only at the sufferance of more advanced beings. While fascinating to contemplate, the hypothesis remains purely speculative and offers no obvious way to distinguish it from the simpler explanation that we are alone. Popular culture has long been fascinated by the idea that alien visitors have already reached Earth, and that evidence of their presence has been hidden by government conspiracies. Ancient astronaut theories propose that mysterious archaeological sites or mythological accounts represent evidence of past alien contact. However, mainstream archaeology and anthropology find no credible evidence supporting these ideas. The remarkable achievements of ancient civilizations can be understood through conventional historical and technological development without invoking extraterrestrial intervention. More recently, government reports on unidentified aerial phenomena have renewed public interest in the possibility of alien visitation. The 2021 report from the Office of the Director of National Intelligence and subsequent reports from the All-Domain Anomaly Resolution Office have acknowledged numerous observations of objects displaying flight characteristics that current human technology cannot easily explain. However, these reports have also emphasized that unknown does not necessarily mean alien. Most UAP reports likely have conventional explanations involving natural phenomena, instrumental artifacts, or classified human technology. The small fraction of cases that remain genuinely puzzling after investigation might eventually yield to better data collection and analysis, rather than requiring exotic explanations. The scientific approach to these reports involves careful documentation, instrumental verification, and systematic analysis to distinguish genuine anomalies from more mundane explanations. As of September 2025, no UAP investigation has produced compelling evidence for extraterrestrial technology, though investigations continue and public interest remains high. Meanwhile, systematic searches for extraterrestrial intelligence continue to expand in scope and sophistication. The SETI Institute and other organizations monitor millions of stars across multiple wavelengths, searching for artificial signals that might indicate the presence of technological civilizations. Projects like Breakthrough Listen process enormous amounts of data from radio telescopes around the world, looking for narrowband signals, unusual modulation patterns, or other signatures that would be difficult to produce through natural processes. These searches have produced occasional interesting signals that initially appeared artificial, but follow-up observations have invariably found natural explanations or traced the signals to human-made interference. The famous WOW signal detected in 1977 remains unexplained, but its failure to repeat despite decades of targeted searches suggests it was likely a transient natural phenomenon rather than an alien transmission. Optical SETI programs search for brief laser pulses or other artificial optical signals, while newer approaches look for mega-scale engineering projects like Dyson spheres or other indicators of advanced civilizations' energy consumption. The absence of positive results so far might simply reflect the limitations of our current search capabilities, or it might indicate that detectable alien civilizations are indeed rare or non-existent in our galactic neighborhood. Even apparently biological mysteries usually yield to more conventional explanations upon careful investigation. The red rain that fell in Kerala, India in 2001 initially generated speculation about possible extraterrestrial microorganisms. However, detailed analysis traced the coloration to airborne spores from local algae, specifically Trentipolia species that commonly grow on trees in the region. The unusual weather patterns that caused these spores to be swept up and concentrated in raindrops created a striking phenomenon that was entirely terrestrial in origin. Such episodes remind us that extraordinary claims require extraordinary evidence, and that our pattern-seeking minds can sometimes interpret unusual natural phenomena as signs of alien activity. The scientific approach involves considering all possible explanations, testing hypotheses through observation and experiment, and remaining open to revision when new evidence becomes available. As our search capabilities continue to improve and our understanding of planetary formation and biological evolution deepens, we may eventually find definitive answers to questions about alien life and intelligence. Whether that answer confirms our cosmic solitude or reveals a universe teeming with life, the discovery will fundamentally change our understanding of our place in the cosmos. For now, we remain suspended between possibility and silence, continuing to search while acknowledging that the absence of evidence is not necessarily evidence of absence. The next signal we detect, the next unexplained phenomenon we investigate, or the next world we study might finally answer the ancient question of whether we are alone. Until then, we continue listening to the cosmos, hoping that somewhere among the countless stars, someone might be listening back. Origins of Earth and life. We have always assumed that Earth's water came from somewhere else, delivered by asteroids and comets during our planet's violent youth. But the more we study the isotopic signatures of different solar system objects, the more complex this delivery story becomes. Water molecules contain varying ratios of ordinary hydrogen to deuterium, its heavier isotope, and these ratios serve as fingerprints that reveal where different water sources originated. Earth's oceans have a specific deuterium to hydrogen ratio that we can compare with measurements from comets, asteroids, and other solar system bodies. The results paint a picture of multiple delivery mechanisms rather than a single source. Many comets from the outer solar system contain water that is significantly enriched in deuterium compared to Earth's oceans, suggesting they cannot be the primary source of our planet's water. However, some comets, particularly those from the Jupiter family that originated in the Kuiper belt, show deuterium ratios much closer to terrestrial values. Carbonaceous asteroids, remnants from the outer regions of the early solar system, also carry water with isotopic signatures similar to Earth's oceans. This suggests that Earth's water likely came from a mixture of sources, some from comets that formed in cold, distant regions of the early solar system, and some from asteroids that accreted water ice and later delivered it through impacts. Additional water might have been present in the original materials from which Earth formed, trapped in minerals, and later released through volcanic outgassing as our planet heated up. Recent measurements from missions to comets and asteroids continue to refine this picture, but each new result seems to add complexity rather than simplicity. The story of Earth's water remains an active area of research, with implications for understanding how other potentially habitable worlds might acquire the liquid water necessary for life as we know it. Even more speculative is the idea of panspermia, the hypothesis that life or its building blocks might travel between worlds on meteorites, comets, or other natural spacecraft. This concept takes several forms, from the relatively conservative idea that organic molecules necessary for life could survive interplanetary transport to the more exotic suggestion that actual living microorganisms might traverse the vast distances between star systems. The basic chemistry version of panspermia has considerable support. We know that space contains complex organic molecules, from simple compounds like methanol and formaldehyde to more complex structures like amino acids and even simple sugars. Meteorites regularly deliver these compounds to Earth, and similar processes likely occurred throughout the early solar system when impact rates were much higher. More challenging is the idea that actual living organisms could survive the extreme conditions of space travel, including intense radiation temperature extremes and the near-perfect vacuum between worlds. Some Earth organisms, particularly certain bacteria and tardigrades, can survive remarkable conditions including exposure to space, but whether they could remain viable during journeys lasting millions of years across interplanetary or interstellar distances remains highly uncertain. The definitive test for panspermia would be finding unambiguously alien life that shares no common evolutionary history with Earth organisms. If life on Mars or other worlds shows completely different biochemistry, using different amino acids, different genetic codes, or different basic cellular structures, it would strongly suggest independent origins. If, however, alien life shows remarkable similarities to Earth life, it might indicate either panspermia or simply that the basic chemistry of life naturally converges on similar solutions. One of the most catastrophic events in Earth's history provides a dramatic example of how cosmic impacts can reshape planetary evolution. The Chicxulub impact 66 million years ago, which likely contributed to the extinction of non-avian dinosaurs, left a crater 180 kilometers across beneath Mexico's Yucatan Peninsula. Recent drilling into this crater has revealed remarkable details about one of the most violent events in our planet's history. The impact generated temperatures hot enough to vaporize rock, created massive tsunamis that raced across shallow seas and threw enormous amounts of debris into the atmosphere. This debris likely blocked sunlight for months or years, causing global cooling and the collapse of food chains. The chemical analysis of crater rocks shows evidence for the rapid formation of the crater's peak ring, a process that occurred in just minutes during the immediate aftermath of the impact. Perhaps even more fundamental to Earth's existence is the origin of our unusually large moon, which likely formed through a giant impact between the early Earth and a Mars-sized object astronomers call Theia. This collision would have been far more violent than the Chicxulub event, potentially melting both objects completely and creating a debris disk from which the moon later coalesced. The giant impact hypothesis explains many features of the Earth-Moon system, including the moon's relatively small iron core, the high angular momentum of the system, and the fact that moon rocks returned by Apollo missions show oxygen isotope ratios nearly identical to Earth's mantle. However, this isotopic similarity creates its own puzzle. Computer simulations of giant impacts typically predict that the moon should be composed primarily of material from the impactor rather than from Earth, yet the isotopic evidence suggests the two bodies are nearly identical in composition. Recent models have proposed solutions involving more exotic impact scenarios, such as the formation of a synestia, a donut-shaped cloud of vaporized rock that might allow thorough mixing of material from both colliding bodies. These new models remain speculative, but they illustrate how even well-established theories continue to evolve as new evidence emerges. Earth's magnetic field, generated by convection in our planet's liquid iron core, has played a crucial role in protecting our atmosphere from erosion by the solar wind. This magnetic shield occasionally reverses itself, with north and south magnetic poles switching positions in a process that can take thousands of years to complete. During these reversals, the magnetic field weakens significantly, potentially allowing increased cosmic radiation to reach Earth's surface. The geological record shows that magnetic reversals have occurred hundreds of times throughout Earth's history, with the frequency varying considerably over geological time. Some periods show reversals every few 100,000 years, while others remain stable for tens of millions of years. Despite popular concerns, there is no convincing evidence that magnetic reversals have caused mass extinctions or other biological catastrophes, though they might have contributed to evolutionary pressures during certain periods. Among the most ancient materials found on Earth are tiny mineral grains that actually predate our solar system entirely. These pre-solar grains, recovered from meteorites, formed in the atmospheres of dying stars billions of years before our sun was born. They carry isotopic signatures that are completely unlike anything produced in our solar system, preserving information about stellar nucleosynthesis processes that occurred in ancient stars. Silicon carbide grains represent some of the most common pre-solar materials created in the carbon-rich atmospheres of dying stars and somehow surviving the violent processes that formed our solar system. Analysis of these microscopic time capsules has revealed details about supernovae, red giant stars, and other stellar processes that occurred when our galaxy was much younger and had a very different chemical composition. The survival of these delicate grains through the turbulent formation of our solar system seems almost miraculous. They endured the collapse of molecular clouds, the formation of the protosolar disk, and incorporation into asteroids and comets, somehow maintaining their distinctive isotopic signatures throughout billions of years of cosmic evolution. Perhaps one of the most controversial claims about ancient life involves the Martian meteorite ALH-84001, discovered in Antarctica in 1984. Initial studies suggested this rock blasted off Mars by an ancient impact and eventually landing on Earth might contain fossilized evidence of ancient Martian life in the form of microscopic structures resembling bacteria. However, decades of subsequent analysis have failed to confirm this interpretation. The structures in question can be explained through non-biological processes, and no other Martian meteorites have yielded similarly suggestive evidence. While ALH-84001 remains scientifically valuable for understanding Martian geology and the possibility of past water activity on Mars, it no longer represents compelling evidence for extraterrestrial life. This episode illustrates both the excitement and the challenges involved in searching for signs of ancient life, whether on Earth or other worlds. Distinguishing genuine biological signatures from similar-looking geological processes requires extremely careful analysis and multiple lines of evidence. Even then, extraordinary claims about extraterrestrial life require extraordinary evidence that can withstand the most rigorous scrutiny. The search for life's origins on Earth continues to focus on understanding how complex organic chemistry could have emerged from simpler chemical precursors in the conditions present on the early Earth. Laboratory experiments have shown that many of life's basic building blocks can form spontaneously under a variety of conditions, but the transition from chemistry to biology, the emergence of self-replicating systems capable of evolution, remains one of science's greatest unsolved puzzles. Different hypotheses focus on different aspects of this transition. The RNA world hypothesis suggests that ribonucleic acid, which can both store information like DNA and catalyze chemical reactions like proteins, might have been the first self-replicating molecule. The metabolism first hypothesis proposes that networks of chemical reactions similar to those found in living cells could have emerged first, with genetic replication systems developing later. More recent ideas focus on the role of mineral surfaces, hydrothermal vents, or other environmental factors that might have concentrated organic molecules and catalyzed the chemical reactions necessary for life's emergence. Each approach offers insights into possible pathways from chemistry to biology, but none has yet produced a complete, convincing explanation for how life began. These questions about life's origins connect directly to our search for life elsewhere in the universe. If life requires extremely specific conditions or unlikely chemical pathways, then biological activity might be vanishingly rare in the cosmos. If alternatively life emerges readily from common chemical processes, then the universe might be teeming with biological activity, most of it probably very different from the carbon-based, water-dependent life we know on Earth. As we continue studying the origins of our planet, our moon, our oceans, and life itself, we are essentially reading the historical record of cosmic and biological evolution. Each isotopic measurement, each ancient mineral grain, each fossil microorganism, and each laboratory experiment adds another piece to the vast puzzle of how we came to exist in this particular place at this particular time. The story that emerges is one of cosmic violence and chemical creativity, of catastrophic impacts and delicate molecular processes of destruction and creation operating hand in hand over billions of years. Understanding this story helps us appreciate both the remarkable sequence of events that led to our existence and the possibility that similar sequences might have occurred elsewhere in the universe, perhaps leading to forms of life we have never imagined. Strange planetary histories. We have always pictured Venus as Earth's evil twin, a world that chose the path of runaway greenhouse warming, while our planet found the perfect balance for life. But recent climate modeling suggests that Venus might once have been far more Earth-like than we ever imagined. Some sophisticated general circulation models indicate that if Venus had rotated more rapidly in its early history, it could have maintained temperate surface conditions with liquid water oceans for billions of years. The slow rotation we observe today, with Venus taking 243 Earth days to complete one rotation, creates extreme day-night temperature differences that contribute to the planet's current hellish conditions. A faster spinning early Venus might have developed cloud patterns and atmospheric circulation that could have kept surface temperatures cool enough for water to remain liquid. This hypothetical temperate period could have lasted for several billion years before tidal forces from the sun gradually slowed Venus's rotation, eventually triggering the runaway greenhouse effect that created the 450 degrees Celsius wasteland we see today. Other models argue that Venus was likely hot and dry from very early in its history due to its proximity to the Sun and the physics of atmospheric water loss. In this scenario, any water Venus might have possessed early in its history would have been rapidly lost to space through photodissociation and hydrogen escape, leaving the planet dry long before complex atmospheric evolution could occur. The debate has profound implications for our understanding of planetary habitability and the search for life around other stars. If Venus was once habitable, then planets in Venus-like orbits around other stars might represent a much larger population of potentially life-bearing worlds than current models suggest. The upcoming Da Vinci Veritas and Envision missions to Venus should provide crucial data to help resolve this fundamental question about our neighboring world's history. The architecture of our solar system itself bears the scars of a violent rearrangement known as planetary migration. The Nice model, named after the French city where it was developed, proposes that the giant planets formed in much more compact orbits than they occupy today, and then migrated outward through gravitational interactions with a massive disk of planetesimals. During this migration, Jupiter may have temporarily moved inward toward the Sun before reversing course and migrating outward again, a scenario known as the Grand Tack model. This inward then outward migration could explain why Mars is so small compared to Earth and Venus. Jupiter's gravitational influence might have prevented Mars from accreting as much material during its formation. The migration of the giant planets also scattered countless small bodies throughout the solar system, potentially triggering the late heavy bombardment around 4 billion years ago, when the inner planets experienced a surge of crater-forming impacts. This bombardment might have been crucial for delivering water and organic compounds to Earth and other terrestrial planets, but it also represents a period of cosmic violence that any emerging life would have had to survive. Modern versions of planetary migration models have become increasingly sophisticated, incorporating detailed simulations of gravitational interactions, collisional evolution, and the complex feedback between migrating planets and the debris disks that surrounded them. Each refinement reveals new subtleties in how planetary systems evolve and helps explain the remarkable diversity of exoplanetary systems discovered by missions like Kepler and TESS. The concept of ocean worlds has expanded dramatically beyond Earth to include numerous moons and even some of the most distant objects in our solar system. Europa and Enceladus have become poster children for potentially habitable environments, but they represent just the beginning of a much larger population of worlds that might harbor subsurface oceans. Ganymede, Jupiter's largest moon, likely contains more water than all of Earth's oceans combined in a subsurface ocean sandwiched between layers of ice. Callisto, Titan, and even distant Pluto show evidence for possible subsurface oceans maintained by various combinations of tidal heating, radioactive decay, and gravitational interactions. Even tiny Mimas, one of Saturn's smaller moons, has recently emerged as a candidate ocean world based on subtle variations in its orbital motion. The realization that ocean worlds might be common throughout the solar system has revolutionized astrobiology and the search for life beyond Earth. These hidden oceans, protected from space radiation by kilometers of overlying ice and potentially maintained for billions of years through internal heating, might represent the most common type of habitable environment in the universe. If life can thrive in these dark, pressurized oceans, then the number of potentially inhabited worlds in our galaxy might be orders of magnitude larger than estimates based solely on planets in the traditional habitable zones around their stars. Ocean worlds could exist around virtually any star, regardless of the distance that would make surface water impossible. Saturn's rings present another puzzle about violent transformation in planetary systems. These spectacular structures appear to be much younger than the solar system itself, perhaps only a few 100 million years old based on measurements of their mass and contamination by darker material. This youth poses a puzzle. What process created Saturn's rings so recently in cosmic terms? One intriguing hypothesis suggests that Saturn once possessed an additional moon dubbed Chrysalis by researchers that orbited just outside the current ring system. Gravitational interactions with other moons could have driven Chrysalis into an unstable orbit, eventually causing it to spiral inward and be torn apart by Saturn's tidal forces. The debris from this disrupted moon could have formed the rings, while also explaining Saturn's unusual axial tilt through the gravitational perturbations that preceded the moon's destruction. This scenario remains speculative, but it illustrates how planetary systems might continue to evolve catastrophically, even billions of years after their initial formation. The rings of Saturn, rather than being primordial features, might represent a recent cosmic accident that we happen to be witnessing during the brief period when they remain visible. The traditional story of the late heavy bombardment, a surge of impacts that allegedly struck the inner solar system around 4 billion years ago, has come under increasing scrutiny as new evidence has emerged from lunar samples and asteroid missions. Some researchers now question whether this bombardment was a discrete event or simply the tail end of the more general process of planetary formation. Evidence from different sources tells conflicting stories about impact rates in the early solar system. Lunar samples from Apollo missions show a concentration of impact melt rocks with ages around 4 billion years, supporting the idea of increased bombardment during this period. However, asteroid samples returned by missions like Hayabusa and OSIRIS-REx show more complex impact histories that don't clearly support a discrete bombardment event. The debate matters because the late heavy bombardment has been invoked to explain everything from the delivery of water to Earth to the timing of life's emergence in the geological record. If the bombardment was less dramatic than originally proposed, or if it occurred at different times for different regions of the solar system, then many assumptions about early planetary evolution might require revision. These mysteries about planetary histories remind us that even our own solar system, the planetary system we know best, continues to surprise us with evidence for complex and violent evolution over billions of years. From a potentially habitable ancient Venus to migrating giant planets to recently formed ring systems, the worlds around us preserve a record of processes that shaped not just our cosmic neighborhood, but potentially countless other planetary systems throughout the galaxy. Each new mission and observation reveals additional layers of complexity in planetary evolution, additional ways that worlds can form, migrate, collide, and transform over cosmic time. As we discover thousands of exoplanetary systems with architectures very different from our own, understanding the strange histories of our solar system's worlds becomes crucial for interpreting the diversity of planetary outcomes possible in the universe. Physics that stretches the mind. We have always assumed that the fundamental constants of physics represent absolute truths about reality, unchanging pillars that support the structure of space and time. But modern physics reveals phenomena so strange that they challenge our most basic assumptions about the nature of existence itself. Time dilation, predicted by Einstein's theory of relativity and confirmed by countless experiments, demonstrates that time is not the universal constant we experience in daily life. Every GPS satellite in orbit around Earth must correct for relativistic effects, running their clocks slightly faster to compensate for the weaker gravitational field they experience compared to receivers on the surface. Without these corrections, navigation systems would accumulate errors of several kilometers per day. Laboratory experiments with atomic clocks have confirmed time dilation effects even more precisely. Clocks flown on airplanes run slightly slower or faster than identical clocks on the ground, depending on their altitude and speed, exactly as Einstein's equations predict. These effects, once purely theoretical curiosities, now represent essential corrections for technologies we use every day. The implications stretch far beyond practical applications. Time dilation means that time itself is relative, dependent on motion and gravity in ways that violate our intuitive understanding of simultaneity and causation. Events that appear simultaneous to one observer occur at different times for observers in relative motion. The universe possesses no universal now that all observers can agree upon. Even stranger is the fate that awaits our universe according to current observations of cosmic acceleration. The discovery that dark energy is driving an ever faster expansion suggests several possible endings for everything we know. The most likely scenario given current data is the Big Freeze, where expansion continues forever while stars burn out, black holes evaporate, and the universe approaches a state of maximum entropy and minimum temperature. But recent preliminary results from the Dark Energy Spectroscopic Instrument hint that dark energy might not be perfectly constant after all. If dark energy is evolving over time, it could lead to even more dramatic endings. Phantom dark energy, if it exists, would accelerate expansion so rapidly that it would eventually overcome all other forces, tearing apart galaxies, stars, atoms, and even space-time itself in a Big Rip scenario. Alternatively, if dark energy weakens or reverses sign, the universe could eventually stop expanding and begin contracting, leading to a big crunch that would essentially reverse the Big Bang. More exotic possibilities include cyclic universes that expand and contract repeatedly, or scenarios where our apparently three-dimensional space is actually part of a higher dimensional structure undergoing complex evolution. These possibilities remain speculative, dependent on physics we do not yet understand and observations we have not yet made. But they remind us that our universe's future, like its past, might involve phenomena that stretch our imagination and challenge our assumptions about what is possible. The search for primordial gravitational waves represents another frontier where observation meets the limits of theoretical physics. Cosmic inflation, the period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang, should have generated gravitational waves that left distinctive patterns in the cosmic microwave background radiation. Multiple experimental campaigns, including the BICEP and Keck telescopes at the South Pole and the Planck satellite, have searched for these primordial gravitational wave signatures. So far, the results have been negative or inconclusive, setting increasingly stringent limits on inflation models and ruling out many theoretical scenarios for the early universe. The absence of detected primordial gravitational waves doesn't disprove cosmic inflation, but it does constrain the energy scales and physical processes that could have operated during this crucial epoch. Each improved measurement helps narrow the range of possible inflation models, gradually building a more precise picture of what might have occurred when our observable universe was smaller than a proton. Perhaps the most embarrassing problem in theoretical physics involves the energy of empty space itself. Quantum mechanics predicts that even a perfect vacuum should contain enormous amounts of zero-point energy from virtual particles that briefly pop into existence before annihilating. When physicists attempt to calculate how much energy this quantum vacuum should contain, they get answers that exceed observational limits by factors of 10 to the 60th power, or even 10 to the 120th power. This vacuum energy problem represents the worst disagreement between theory and observation in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or there exist unknown physical processes that cancel out the vacuum energy with extraordinary precision, or the mathematics we use to make these calculations breaks down under conditions we don't yet understand. Various theoretical approaches have attempted to resolve this vacuum energy catastrophe, from supersymmetry to extra dimensions to modifications of quantum field theory itself. None have yet succeeded in providing a convincing explanation that preserves the remarkable successes of both quantum mechanics and general relativity, while explaining why the observed vacuum energy is so much smaller than naive calculations predict. The mystery of antimatter's absence poses another fundamental puzzle about the basic structure of reality. The early universe should have contained equal amounts of matter and antimatter, which would have completely annihilated each other, leaving behind a universe containing nothing but photons. The fact that we exist at all proves that some process must have created a slight excess of matter over antimatter. This process, known as baryogenesis, requires very specific conditions that violate certain symmetries of fundamental physics. Candidate mechanisms include leptogenesis, where the decay of heavy neutrinos creates a matter-antimatter asymmetry, or direct CP violation in interactions involving exotic particles. The discovery of neutrino oscillations has provided some evidence for the kinds of symmetry violations that might be required, but the complete picture remains elusive. Recent experiments at the Large Hadron Collider and other facilities continue searching for additional sources of CP violation and for evidence of the exotic particles that might have driven baryogenesis in the early universe. Each measurement helps constrain possible mechanisms for creating the matter-antimatter asymmetry that made our existence possible. At the highest energies ever observed, cosmic ray particles arriving from space carry energies that exceed anything achievable in human-built accelerators by many orders of magnitude. The Pierre Auger Observatory and other facilities have detected cosmic rays with energies above 10 to the 20th electron volts, carrying as much energy as a well-thrown baseball compressed into a single atomic nucleus. The sources of these ultra-high-energy cosmic rays remain uncertain despite decades of observation. They appear to come from relatively nearby regions of the universe within about 50 million light-years, suggesting that even more distant sources exist, but that their particles lose energy through interactions with background radiation during their journey to Earth. Candidate sources include active galactic nuclei, gamma-ray bursts, and colliding black holes, but none perfectly matches all the observed properties of ultra-high-energy cosmic rays. The particles' composition, arrival directions, and energy spectrum all carry clues about their origins and the extreme processes that accelerated them to such remarkable speeds. These phenomena at the frontiers of physics remind us that reality operates according to principles that often contradict our everyday experience, and sometimes even our most sophisticated theoretical understanding. From the relative nature of time to the mystery of vacuum energy, from the absence of antimatter to cosmic rays carrying impossible energies, the universe continues to present us with puzzles that push the boundaries of human knowledge and imagination. Each unsolved problem in fundamental physics represents not just a gap in our understanding, but an opportunity to discover new principles that might revolutionize our comprehension of space-time, matter, and energy. The next breakthrough in physics might come from resolving any one of these mysteries, potentially opening entirely new realms of knowledge and possibility. Unsolved spacecraft and solar mysteries. We have always trusted that our spacecraft follow predictable trajectories determined by well-understood gravitational forces, but several space missions have exhibited subtle anomalies that continue to puzzle engineers and physicists decades after their discovery. The Pioneer anomaly captivated researchers for years with its suggestion that something was gently but persistently pulling the Pioneer 10 and 11 spacecraft off their expected trajectories. As these robotic explorers journeyed toward the outer reaches of the solar system, careful tracking revealed that they were slowing down by a tiny amount, about 1/10,000,000th of a meter per second squared, more than gravity alone could explain. This minuscule acceleration, persistent over decades of observation, sparked intense debate about possible exotic explanations. Some researchers wondered whether it might indicate a breakdown of Newton's law of gravity at very large distances, or perhaps the influence of dark matter concentrated in the outer solar system. More exotic possibilities included modified inertia effects or even systematic errors in our understanding of time and space. The solution, when it finally emerged, proved both more mundane and more technically sophisticated than many had expected. Detailed thermal modeling showed that the spacecraft themselves were creating the anomalous acceleration through the uneven emission of infrared radiation. Heat from the spacecraft's radioactive power sources was being radiated preferentially in directions that created a tiny but measurable rocket effect, gently pushing the craft off their gravitational trajectories. This resolution demonstrates the importance of considering all possible sources of systematic error, no matter how small, when investigating apparently anomalous phenomena. The Pioneer anomaly also illustrates how extraordinary claims require extraordinary evidence, and how patient, careful analysis usually reveals conventional explanations for seemingly mysterious observations. However, other spacecraft anomalies remain genuinely unexplained. Several Earth flyby maneuvers have produced small but measurable changes in spacecraft velocities that cannot be accounted for by known gravitational effects or spacecraft operations. These flyby anomalies involve energy changes of just a few millimeters per second, but they represent genuine discrepancies between prediction and observation that have resisted explanation for decades. The Galileo Near and Rosetta missions all experienced these unexplained velocity changes during gravity-assist flybys of Earth. The changes are small enough that they don't affect mission operations, but large enough to be clearly detectable and inconsistent with current models of spacecraft dynamics. Various explanations have been proposed, including atmospheric drag tidal effects or even subtle errors in the Earth's gravitational field models used for trajectory calculations. What makes these anomalies particularly intriguing is their apparent unpredictability. Some Earth flybys produce the expected results, while others show small discrepancies with no obvious pattern to distinguish between normal and anomalous encounters. This inconsistency makes it difficult to develop theoretical explanations or to design experiments that might resolve the mystery. The careful, skeptical approach taken by the spacecraft navigation community provides an excellent model for investigating anomalous phenomena. Rather than immediately invoking exotic physics, researchers systematically examine all conventional explanations, scrutinize their measurement techniques, and attempt to reproduce anomalous results with independent observations. Only when conventional explanations have been exhausted do they consider more speculative possibilities. Meanwhile, the Sun itself continues to present fundamental mysteries despite being the most studied star in the universe. For decades, measurements of solar neutrinos, nearly massless particles produced by nuclear fusion in the Sun's core, detected only about 1/3 as many as theoretical models predicted. This solar neutrino problem suggested either serious flaws in our understanding of stellar physics or missing pieces in the puzzle of neutrino behavior. The resolution came through the discovery of neutrino oscillations, the phenomenon where neutrinos change from one type to another as they travel from the sun's core to Earth-based detectors. The Sudbury Neutrino Observatory provided the crucial measurements showing that the missing neutrinos had simply transformed into different varieties that earlier experiments couldn't detect. This discovery earned the 2015 Nobel Prize in Physics and resolved one of the most persistent puzzles in solar physics. But the sun retains other secrets that continue to perplex solar physicists. The solar corona, the sun's outer atmosphere visible during total eclipses, reaches temperatures of millions of degrees, despite being farther from the sun's nuclear furnace than the much cooler photosphere beneath it. This temperature inversion violates our intuitive understanding of heat flow and requires exotic heating mechanisms to maintain. Current evidence suggests that the corona's extreme temperatures result from a combination of magnetic reconnection events called nanoflares and the dissipation of Alfvén waves, magnetic oscillations that carry energy outward from the sun's interior. NASA's Parker Solar Probe and the European Solar Orbiter are providing unprecedented measurements of coronal heating processes, but the relative importance of different mechanisms remains debated. The process of magnetic reconnection itself, fundamental to coronal heating, and many other astrophysical phenomena, has been studied in exquisite detail by NASA's magnetospheric multiscale mission. This quartet of spacecraft has measured magnetic reconnection at the electron scale, revealing how magnetic field lines break and reconnect to release vast amounts of stored energy in just milliseconds. These observations show that magnetic reconnection occurs much faster than classical theories predicted, suggesting that small-scale processes involving individual electrons play crucial roles in large-scale magnetic phenomena. Understanding reconnection is essential for predicting space weather events that can damage satellites, disrupt communications, and create beautiful auroras in Earth's polar regions. The complex physics of space plasmas, ionized gases that exist throughout the solar system, continues to reveal new phenomena that challenge our theoretical understanding. Solar wind interactions with planetary magnetospheres create shock waves, magnetic turbulence, and particle acceleration processes that operate on scales from individual particle motions to planetary-sized current systems. These space plasma processes affect everything from the aurora that dance across polar skies to the radiation environment that spacecraft must survive during interplanetary journeys. Predicting space weather requires understanding plasma physics under conditions that cannot be replicated in laboratory settings, making space-based observations crucial for advancing both basic science and practical applications. As our ability to measure spacecraft trajectories and solar phenomena becomes increasingly precise, we continue to discover small discrepancies between theory and observation that hint at gaps in our understanding. Some of these anomalies, like the Pioneer effect, yield to patient analysis and reveal the importance of considering all physical processes, no matter how subtle. Others, like the flyby anomalies, remain genuinely mysterious and continue to challenge our theoretical understanding. The approach taken by spacecraft navigation teams and solar physicists, careful measurement, systematic analysis, and skeptical evaluation of extraordinary claims, provides a model for investigating any apparently anomalous phenomena. Science progresses through the gradual accumulation of precise observations and the development of theoretical frameworks that can account for increasingly subtle effects. Whether studying spacecraft dynamics or solar physics, researchers must balance openness to new discoveries with healthy skepticism about claims that challenge well-established understanding. The next breakthrough might come from resolving one of these persistent anomalies, or it might emerge from discovering entirely new phenomena that current theories cannot explain. Conspiracies, legends, and unsolved tales. We have always been drawn to stories that suggest reality is more mysterious and conspiratorial than it appears on the surface. But distinguishing genuine scientific mysteries from cultural myths requires careful attention to evidence and a willingness to separate what we want to believe from what the data actually supports. Recent headlines about the James Webb Space Telescope finding galaxies that are too old or too massive for current cosmological models illustrate how scientific discoveries can be sensationalized and misinterpreted. When JWST first began operations, some early observations suggested galaxies at high redshifts that appeared more massive than models predicted, leading to dramatic claims about cosmological crises and the need to abandon our understanding of the universe's evolution. However, as spectroscopic measurements have refined the distances and masses of these early galaxies, the apparent crisis has largely dissolved. Many objects initially thought to be extremely distant and massive have been revealed to be closer and less exceptional than first estimates suggested. The process illustrates how preliminary observations can be misleading and why extraordinary claims require extraordinary evidence that can withstand detailed scrutiny. The genuine discoveries about early galaxy formation remain scientifically exciting even without revolutionary implications. JWST has indeed found that galaxies formed earlier and grew more rapidly than many models predicted, but these findings represent refinements to our understanding rather than fundamental challenges to cosmology. Science progresses through such adjustments and improvements rather than dramatic paradigm shifts. Similarly, the discovery of galaxies with apparently little or no dark matter has generated considerable excitement and speculation about the nature of cosmic structure formation. Objects like NGC 1052, DF2, and DF4 appear to contain far less dark matter than typical galaxies of their size, challenging our understanding of how galaxies form and evolve within dark matter halos. However, these galaxies likely represent rare outliers produced by specific formation processes, rather than evidence against dark matter's existence. They probably formed through tidal interactions that stripped away most of their dark matter while leaving stars behind, creating unusual objects that help us understand the relationship between visible and dark matter under extreme conditions. Rather than breaking our cosmic models, these galaxies provide new tests of how structure formation operates in different environments. The mysterious Black Knight satellite represents a perfect example of how unrelated observations and images can be woven together into a compelling but fictional narrative. This supposed ancient alien probe has become a staple of conspiracy theories and popular culture, supported by a famous NASA photograph that appears to show a dark, artificial-looking object in space. The reality is far more mundane. The iconic image shows a thermal blanket that was accidentally released during a space shuttle mission, not an ancient alien artifact. The Black Knight legend has assembled various unrelated historical reports of unusual radio signals, astronomical observations, and space debris into a single fictional narrative that has no basis in documented fact. It serves as a cautionary tale about how pattern-seeking minds can create elaborate explanations for disconnected events. The hollow moon hypothesis proposed by some fringe theorists based on seismic data from Apollo missions suggests that our natural satellite might be largely empty inside or even artificially constructed. This idea gained traction from the observation that lunar seismic waves propagate differently than earthquake waves on Earth, leading to speculation about unusual internal structure. However, detailed analysis of Apollo seismometer data reveals that the moon's interior structure is well understood and entirely consistent with formation through natural processes. The moon possesses a small iron core, a partially molten mantle, and a solid crust, just as we would expect from a world that formed through accretion and differentiation. The unusual seismic properties result from differences in composition and structure compared to Earth, not from artificial construction or hollow spaces. The famous face on Mars, first imaged by Viking missions in 1976, became one of the most enduring examples of pareidolia, the tendency to perceive meaningful patterns in random or ambiguous stimuli. The low-resolution Viking image showed what appeared to be a humanoid face carved into the Martian landscape, complete with eyes, nose, and mouth features that seemed too regular to be natural. Higher-resolution images from Mars Global Surveyor and Mars Reconnaissance Orbiter have definitively shown that the face is simply an eroded mesa whose resemblance to facial features depends entirely on viewing angle and lighting conditions. Under different illumination, the formation looks nothing like a face and shows clear evidence of natural erosion processes. The episode demonstrates how initial impressions based on limited data can be misleading and how improved observations usually provide more conventional explanations. Ancient petroglyphs and rock art from cultures around the world sometimes depict figures that modern interpreters have labeled as star people or ancient astronauts. These artistic representations found on every continent show humanoid figures with unusual headgear, radiation-like halos, or other features that some have interpreted as evidence of prehistoric contact with extraterrestrial visitors. However, these interpretations typically ignore the cultural and religious context in which the art was created. Most petroglyphs can be understood as spiritual or mythological representations within their original cultural frameworks, depicting shamanic visions, religious ceremonies, or symbolic relationships with natural forces. The tendency to interpret ancient art through modern technological metaphors says more about our contemporary obsessions than about prehistoric realities. Government investigations into unidentified aerial phenomena have produced extensive documentation that is publicly available, contradicting claims of systematic cover-ups or suppression of evidence. The All-Domain Anomaly Resolution Office's comprehensive historical review, released in 2024, examined decades of UAP reports and investigations, finding no credible evidence that any government agency has recovered alien technology or covered up evidence of extraterrestrial visitation. This doesn't mean that all UAP reports have conventional explanations. Many remain genuinely puzzling and worthy of continued investigation. However, the transparency of recent government reports and the systematic nature of ongoing investigations argue against conspiracy theories involving hidden alien technology or coordinated cover-ups across multiple agencies and decades. Claims that ancient pyramids were aligned with stellar constellations like Orion, suggesting advanced astronomical knowledge or alien guidance, face serious challenges when subjected to rigorous analysis. The apparent alignments often depend on selective interpretation of archaeological evidence and fail to account for the effects of stellar proper motion over thousands of years. Most pyramid alignments can be explained through conventional surveying techniques available to ancient civilizations, combined with the basic astronomical observations that any agricultural society would naturally develop. The remarkable achievements of ancient architects and astronomers require no extraterrestrial explanation, though they certainly deserve our admiration and continued study. The persistent claim that NASA airbrushes or otherwise conceals evidence of alien structures in spacecraft images reflects fundamental misunderstandings about how space imaging works. All raw spacecraft data is publicly available through NASA archives, and the image processing techniques used to create publication-quality images are well documented and scientifically necessary to correct for instrumental effects and enhance scientific value. The transformation from raw digital data to final color images involves multiple calibration steps that correct for camera sensitivity, lighting conditions, and atmospheric effects. These processing steps are essential for extracting scientific information and are performed using transparent, documented procedures. Claims of deliberate concealment typically misinterpret normal image processing as evidence of conspiracy. Perhaps the most profound speculation involves the idea that humanity itself might represent some form of cosmic experiment seeded by advanced beings who continue to monitor our development. This scenario, while popular in science fiction, faces the same evidentiary challenges as other claims about alien intervention. Extraordinary assertions require extraordinary proof that has not yet been provided. Such ideas remain in the realm of philosophical speculation, rather than scientific hypothesis, because they make no testable predictions and cannot be distinguished from scenarios involving natural evolution and development. Until we discover compelling evidence for current or past extraterrestrial contact, the simpler explanation that humanity evolved naturally on Earth remains the most scientifically defensible position. As we conclude this journey through cosmic mysteries, we find ourselves suspended between the known and the unknown, between the longing for extraordinary explanations and the discipline of careful investigation. The universe presents us with genuine puzzles that push the boundaries of human knowledge. From dark matter and dark energy to the origins of life and the possibility of intelligence elsewhere in the cosmos, these authentic mysteries provide more than enough wonder and excitement without requiring us to embrace unfounded conspiracy theories or dismiss well-established scientific understanding. The real universe, with its black holes and quantum mechanics, its billions of galaxies and potential for life beyond Earth, offers profound questions that may take generations to answer. Perhaps the greatest mystery of all is consciousness itself, the emergence of self-aware beings capable of contemplating their own existence and seeking to understand the cosmos that created them. Whether we are alone in this quest or part of a larger community of conscious beings scattered throughout the galaxy, remains the ultimate open question. As you drift towards sleep tonight, consider that you are made of elements forged in the hearts of ancient stars, living on a world that harbors life through an intricate balance of cosmic forces, gazing out at a universe that may contain wonders we have not yet learned to imagine. In the face of such genuine mystery and beauty, perhaps our role is simply to remain curious, to keep asking questions, and to approach the unknown with both wonder and wisdom. The cosmos keeps its deepest secrets for now, But it has already revealed enough to remind us that reality is far stranger and more magnificent than any conspiracy or legend we might invent. Rest well knowing that tomorrow will bring new observations, new questions, and new opportunities to edge closer to understanding our place in this remarkable, mysterious universe.